The main objective of this lab was to perform tensile tests on various materials to measure mechanical properties, such as the modulus of elasticity, yield stress, ultimate tensile strength, and percent elongation and reduction of area, using the MTS frame, as well as to analyze the stress-strain data collected. For this experiment, we tested 3 different materials: 4140 steel, grade 2 titanium, and 6061 aluminum. But why is tensile testing important? The information gained from these tests can provide essential data for material selection, design safety, and quality assurance in manufacturing. Watch these tensile tests being performed. Notice the time clocks in the bottom right corners of each video. The titanium bar took the longest before fracture occurred. This specimen also experienced the most necking of the 3 materials. Necking will only begin once the stress-strain curve has reached its maximum stress, or the ultimate tensile strength. You should begin to see necking in the samples about now.
So, looking at our experimental data compared to the standards, we did notice a few key differences. For elastic modulus, our values for aluminum 6061 and titanium grade 2 were slightly lower than the standard, and for the 4140 steel, the modulus was on the lower end of the range. In terms of yield stress, aluminum and titanium closely matched the standards, but the steel was on the higher side at 590 megapascals. For ultimate tensile strength, all of our results were slightly below the standard values. When it comes to elongation, aluminum was more ductile than expected, while the steel had lower elongation than standard. These differences could be due to sample preparation, testing conditions, inexperienced testers, or variations in material batches, all of which influence mechanical properties.
Here we have plots showing the stress versus strain curves for each of our 3 materials. On the left we have engineering stress versus strain, which is calculated by dividing the force by the original cross-sectional area of the bar. This provides us a good estimation of the behavior we can expect, however is not fully representative of what's going on. On the right we take into account the instantaneous change in cross-sectional area to compute the true stress versus strain. As you can see, the stress curves do not follow the extent of strain as the engineering curves on the left. As deformation is a constant volume process, we can reach a point where dramatic necking occurs. At this point, the stress state is no longer uniaxial, and the assumptions we make around uniform plasticity and material flow no longer apply. This occurs around or after the ultimate tensile strength is reached, which we can see correlates with the degree of strain the stress curves end. With that in mind, we can see that the 4140 steel has the highest tensile strength but the lowest elongation. This may make the steel the best choice for a high-strength structural component that requires a certain level of strength we have to design around. Aluminum, on the other hand, has the lowest strength but moderate ductility. Lastly, we have titanium, which has relatively good strength and excellent ductility compared to the steel and aluminum. This leaves us with a large area under the curve, which relates to strain energy density consumed by deforming the material. We refer to this as toughness, and this can indicate the material's resistance to fracture. Having high toughness, the titanium may be a good fit for high cycle fatigue applications where resistance to crack propagation are extremely important.